All right, hello everybody. How's everything going? Uh, Thank you for joining us for this uh, webinar presentation for the MIDAS Micro by Hafley. I'm very excited and I'm glad to see many people showing up for this webinar. My name is Ramon Burgos. I am the HV sales manager here at HV Technologies. I'll be presenting, like I mentioned, the MIDAS Micro, which is Hafley's compact substation mobile insulation diagnosis and analyzing system. Before we get into the slides, I want to mention that there is a chat box uh, up on your team's menu. Up on the top bar, you should have a chat box or a Q&A tab where you can write in your questions or comments, which we will get to later on at the end of the presentation. But for now, we're going to get started with presenting the MIDAS Micro 2883. All right, so the MIDAS Micro 2883 is right now the smallest, most compact insulation tester on the market. It is designed for dissipation factor or power factor, as it is also known, and capacitance testing in the field and in the factory. So with this instrument, it includes all the features needed to perform tests on various high voltage components. It has a 12 kV voltage source that delivers a clean signal, a variable frequency source for advanced measurements or bushing analysis, for example. Uh, it has an internal gas-filled standard capacitor, which guarantees repeatable results and long-term stability. And just to get into some of the basic specs, as you can see on the slide, it's the instrument itself, which you see here on the left-hand side. It comes in at 55 pounds, ultra light for this type of equipment. Um, it comes with the wheels and a pull-out handle, so it's easy to transport, move around. Very important are the high accuracy of this instrument. Also, we have plus or minus 0.3% on your capacitance measurements, and a 1 times 10 to the negative 4 on your dissipation or power factor or 10 delta measurements. Is very important since the 10 delta measurements are usually very small, so it's good to have high accuracy in order to read these very small measurements. Like I mentioned, the 12K up to 12 kV output with a frequency of 15 to 400 hertz. So this unit will be able to manage testing any device up to 39 nanofarads at 60 hertz or 47 nanofarads at 50 hertz. So some of the main features that I want to mention is the one box design at only 55 pounds, has the rugged case with wheels and a handle that you can pull out. Um, like I said, with the integrated casters, transportation is convenient. Test objects in remote locations can be reached easily. Like I said, this instrument can be used in a factory setting, keep it in the factory, or it could be taken easily to a substation setting with very little issue. I mentioned the 20 to 25 volt to 12 kV volt output with the variable frequency. The quick setup and storage has very easy connections with snapping HV connectors and color-coded cables. So we try to minimize connection errors so that tests run more smoothly. All the cables are coming on cable drums. The clamps that are equipped with the instrument are wide opening clamps, so you can connect to most transformers, bushings, capacitors, you name it. And it also has a wide array of accessories that you can also use for temperature and stuff, but we'll get into that later. We also will get into how the three operating modes of the MIDAS Micro. It has three modes: basic mode, guide mode, and advanced mode. We'll get into that later on. But also, the MIDAS Micro allows us to have quick and reliable results. We have reliable because there's noise suppression features, and like I mentioned, the internal reference capacitor is an SF6 gas capacitor, very stable, and this allows for reliable results even in harsh environments. So if you have this instrument out in your substation with high voltage overhead lines, the the instrument has features that will automatically switch on noise suppression to make sure that your measurements are as accurate as possible. So then once you do your measurements, once you have your test, the test results can be printed using the onboard printer. You can store it on the internal storage, or it could be easily transferred to a USB stick in XML or CSV format. A little bit in with instruments that use high voltage, of course, safety is paramount. So the MIDAS Micro also boasts some pretty good safety features, like open ground detection, which basically, if the safety ground of the instrument is not connected, the instrument will not generate high voltage. Also have your emergency stop push button locally on the front panel of the instrument, which will effectively cut the high power generation instantly. We also have standard with the instrument our interlock switch, what's also known as a dead man switch. So the user, before starting the high voltage generation, the user must press the interlock switch button or the foot pedal in order to start the measurement. Once the measurement is underway, you will get a warning sound and a lamp on your touchscreen display. Or you can also opt for, there's also an optional external strobe light that we can offer and connects to the front panel of the instrument and will also turn on to give that additional visual indication that high voltage is being generated, or that the instrument or that the test object is being tested. So one thing I always like about instruments portable instruments that Hafele offers, designed by TEDx, is the front panel of the instrument is always very simple, devoid of too many buttons and switches. The whole instrument is managed through the 7-inch display, and you have your connection for your high voltage ground, your signal, your measurement channels A and B. You also have your guarding point for different applications. It could be used, for example, on transformers to guard stray capacitances. You have your emergency stop push button, and then your high voltage connection, which snaps in, and of course the safety ground, which is not to be confused with the HV ground. So the safety ground is to be connected to a station earth point, and the HV ground is to be connected to, say, the transformer grounding point. Again, with we also have inputs for the interlock, which could be the hand or the foot switch, for the external strobe light, and for temperature sensors in case you're interested in measuring temperature to do real-time temperature correction. So the integrated printer allows you to, like I said, print out your results quickly. You don't have to wait to connect the computer or to transfer. You can quickly print out your results. And also have USB and LAN interfaces for data handling and also connection to a computer. So when you order a MIDAS Micro 2883, you will get the following. You will get your instrument, the one box design, lightweight, 55 pounds. Also, you will get a transportation bag. Now, in this transportation bag, you will have your high voltage cable, 65 feet in length with your clamp, which is this one here with the clamp. You'll have 3 shielded measuring cables with their clamps, which are these over here. A high voltage ground cable, which is the one that goes to the yellow port on the instrument. You will get 2 cable drums, which you can, on one, you can, for example, put your high voltage cables. On the other one, usually you have all 3 measuring cables in one drum, and that you can quickly clean up after a test. The safety interlock hand switch is standard with the supply of the instrument in the transportation bag. You also have mini clamps for maybe smaller DUT and adapters for bushing tabs if you want to do bushing, if you're interested in doing bushing testing. You will, of course, get an operating manual and certificate of calibration, and the extension clamp is also provided in order to um, increase the opening of your clamps. So you can maybe fit over larger bushings or larger transformer bushings or larger terminals. Let's quickly run through some of the accessories that some of them I've already mentioned. We have the safety strobe light. It comes with a magnetic base, so you can affix it to a transformer tank, for example, and that'll provide an extra means of precaution for anybody who could possibly come into the test area. The hand switch can be substituted by a foot switch. So you have 2 options, hand or foot. Comes standard with the hand button. You have different temperature probes and contactless infrared meters. So you can go ahead and determine the tank temperature, air temperature, and humidity. Instead of a clamp, you can also, on your high voltage cable, you can screw in a hook. That sometimes is convenient. You will also get a set of hot flexible bands for your hot collar test or for your guarding circuits. And then if you need adapter cables for standard capacitors, if that's necessary, so you can switch from NEMO 3 to VNC. And also, for those who are interested in liquid or oil test cells, it can also be provided with a test cell for on-site measurement of transformer oil, for example, up to 10 kV. So with this, you have basically a complete setup for dissipation factor and capacitance measurements of basically any device. So as I mentioned, this is an insulation diagnosis and analyzation system. So why do we test insulation? So insulation tests are useful for checking the dielectric properties and the quality of your insulation. Performing these tests at regular time intervals can detect impending insulation failures before they occur. So usually tests are done at factory, and you may get a manufacturer's certificate saying these are the measurements that we took at factory for tan delta and capacitance. And then once you perform these tests at regular intervals, you can start to trend and gauge any change in your capacitance or dissipation factor measurements. And that's how you can determine whether your insulation is nearing impending failure, or if it's something that maybe you can consider that you might want to replace or maintain. So usually bushings and all these insulation systems are affected by the high electrical field strength, as well as thermal and mechanical stresses. And that is what leads to that gradual deterioration of the insulation. And you get results sort of like what's pictured for a motor or a generator. You can have interwinding failures, the winding insulation failures on bushings. You can have just complete failure and transformer. You can also have an example like this one where you have interwinding uh, failures on your transformer. So basically, when we test for dissipation factor and capacitance, we we get the following information from these tests. So capacitance will warn us of partial breakdowns, oil or moisture that can be seeping into the cracks of solid insulation, or it could also warn us of changes in the geometry of a transformer winding. For example, if a transformer experiences a short circuit or a huge big fault current, and there has been a shifting of windings or a deformation to some of the windings, it could also warn of of those changes. Um, and then when we talk about dissipation factor or tan delta, this allows us to gauge the aging or decomposition of the insulation. It can allow us to to warn us about water content in your insulation, port contacts on your conductors or electrodes. It can also warn us of partial discharges that may be occurring within your insulation system, and cracks in a bushing insulation, for example. So we have for the transformer, which is a very typical application, you can do your tan delta measurement for your bushing as well as your winding. And then you can also do capacitance on your winding. And this instrument will also actually let you do measurement of excitation current. So now when we talk about dissipation factor or tan delta or power factor, how it's usually referred to as in North America, um, we're basically talking about the fact that an insulating material, any insulating material, is basically it can be modeled as a capacitor and as a capacitor in an ideal state, but once you factor in the real world factors, the equivalent circuit becomes a capacitor in parallel with a resistor. So once you apply a high voltage, you will have a total current that will be drawn, and this current is split between your capacitive current, which is your normal capacitive current, and your resistive current. This resistive current is what is known as the dielectric loss or the loss factor current. So in any real world setting, we will have a very small losses in your insulation system. Now, if you see the graph here on the right hand side, although this is exaggerated just for clarity, but this is how your vectors for your currents will be presented, or are this is how the insulation behaves on a vector diagram. So you'll have your capacitive current, which always will lead your voltage signal by 90 degrees. And then you'll have any resistive current, which will be in phase with your voltage. So as this resistive current increases, it pushes your total current away from the y-axis. So you have essentially a generation of an angle between your capacitive current and your total current. This angle is known as the tangent. Similarly, when we talk about power factor, we're talking about this angle between the resistive current and the total current. So that'll give this angle phi. And so basically tan delta is the the ratio between your resistive current, this vector, if we place it over here, it'll be the tangent of this angle, and we will get your resistive current over your capacitive current. That would be tan delta. So we're talking about your resistive power over your react. Now, in power factor, basically, when we think, like I said, these values are usually very small. We're talking about, for example, in a transformer, a good transformer has 0.5% tan delta value. So we're talking about 0.005 tan delta value. So we're talking that the resistive vector is usually very close to this y-axis. And so when we talk about the difference between power factor and tan delta, there really isn't a big difference. The only difference is the angle that is being chosen to evaluate. But is, as you can appreciate in this vector diagram, the angles are complementary. You have tan delta here and whatever, and cosine and phi over here, and they are complementary. So when you have a small tan delta, you basically will have the same value if you take the cosine of this larger phi angle. So for these small insulation measurements, uh, we can say that basically tan delta and power factor are more or less giving the same information. There are some, as you can see in the bottom, there are some formulas that will do the conversion between tan delta and power factor if necessary. But basically, that is what we're looking for. We're looking for this deviation of this total current due to the effect of your resistive current. So some typical capacitances of some devices, you have some bushings will have anywhere between 80 picofarads to 1.2 nanofarads. Transformers from 400 picofarads to 30 nanofarads. So with the MIDAS, you can basically uh, test any bushing or transformer. Then when we get to generators and motors, it gets a little bit more complicated because the capacitance values are a bit higher. So a generator or motor or rotating machines will have anywhere between 10 nanofarads and 2 to 3 microfarads. And then, of course, we can also test cables, which have a standard, we'll say a rule of thumb capacitance of 150 nanofarads per kilometer. So when we want to talk about we've been talking about transformers, bushings, and now we mentioned cables, and we're talking about capacitance. We have to understand how these capacitances in these different devices or components, or what we call specimens, how they are modeled. For example, in a capacitive graded bushing, you have a center conductor, and then you have layers of paper, oil impregnated paper, and this is built up, and so you'll have a series of capacitances that will make up the total capacitance of a bushing. And then you also have a capacitive element when it comes to your bushing tap. So in a bushing, you'll have two different types of capacitances that you will usually measure. On a two-winding transformer, for example, you have your high voltage winding and a low voltage winding. This is a very typical application. And so the capacitances that we model in a two-winding transformer exist between your high voltage and your low voltage winding, and also exist from your high voltage winding to the ground and your low voltage winding to the ground. So for a two-winding transformer, essentially you're going to be making 3 measurements to test your capacitance and dissipation factor. For other specimens such as cables, you have more capacitances that are built in, that are modeled. For example, you'll have your intercable from one cable to another. In this case, for cable 1 to 2, from 2 to 3, and from 3 to 1. So you have 3 measurements that you will do for in this case a 3-phase cable to shield. I'm sorry, unshielded cable, and then you also have from each individual cable to ground. So you have a total of 6 measurements that you will need, for example, on a 3-phase unshielded cable. So once you identify which capacitances in your specimen you will be you will be trying to measure, then it's very important that we discuss, because as you notice, there are some that are down to ground and some that are not. So it's important to mention the different test modes associated with tan delta and capacitance measurement. So basically, we have 2 test modes when we do these types of measurements. We have one, the UST or ungrounded specimen test. We also have the GST or the grounded specimen test. So basically, any capacitance that is being measured from a winding, for example, to ground, or from a cable cord to ground, you will test with a GST specimen, grounded specimen test. You will select that mode on the instrument, and you will do your connections considering that you're doing a grounded test. For any interwinding, like in this case, in this figure, we have 3 winding transformers. So we have a high, low, and a tertiary winding. So for the interwinding capacitances, you will use the ungrounded specimen test, which makes a lot of sense. You have some that go to ground, you use your GST, and others that do not go to ground and will be measured using your UST or ungrounded specimen test. And then what this figure really quickly, what I'm trying to model here or show here is the instrument, depending on your mode, whether you choose UST or GST, internally, that's how he chooses to switch each input and where he will direct the current through these shunts to be processed by the different components and go through the calculation algorithms and whatnot. So it's very important to understand what your capacity, what you want to measure, and how you should go about measuring it. Like I said, like I mentioned earlier, the simplicity of the management of the instrument is always good to have for operators. It's in the MIDAS micro I mentioned, we have 3 modes of doing measurements: basic, guided, and advanced. The home screen will give you those 3 options, as well as a tab that you can see all your measurement results, and a tab to set up the specimen or device that you are going to test. So when you choose basic mode, so the basic mode allows for just simple, fast manual measurement. First, you will define the test parameters, and then you press start, and it will go ahead and do the measurement. As soon as it reaches a stable reading, it'll shut down the high voltage, and then the results will be recorded in this table below. So basically, what you in basic mode, you already have a sense. So you say, yeah, maybe I want to test the capacitance high voltage to low voltage winding. So you know you're going to use a UST. So you go ahead, select first your test voltage. You select your test frequency. Then you select your test mode. So if we want to do interwinding, we do UST mode. And then by pressing this button here, you can choose whether you want to use your A signal cable to be included in the measurement, or your B signal cable, depending on how you use do your test connections. All the values that are these values here that you can see these arrows pointing down. These are the different values these are drop down menus or menus that you can press and you can choose which values you want to see and record at that moment. So you can choose, and usually you'll have one for tan delta, one for capacitance, and here you can do frequency or you can do inductance. There's a whole list of different measurement options that you can choose. So this is basically a one-shot test, easy, simple, fast, not too much science to it. When we get into guide mode is probably what my preferred mode. The guide mode basically is a wizard that'll lead you through the test setup of the measurement. It'll lead you through selection of the type of DUT, as well as the selection of the type of measurements you want to perform. And so when you define your device, whether it be a 2-winding transformer or a 3-winding transformer or a bushing, it'll give you this sub menu, and you can choose what you want to test. So if we wanted to do just capacitance and dissipation factor, we'll choose capacitance and dissipation factor. We'll set what our voltages will be for each winding, in this case for a 2-winding transformer. And then you can hit start, and it'll switch to what I like to call like a playbook, like if we're playing on a team sport. This is the playbook. This is how it'll show you how to connect your high voltage, your ground, and your measuring or your signal cable, and it'll show you, it'll guide you step by step through each step, so you can go ahead and make sure you have the correct measurements for each capacitance associated with your device. Now, if you're very experienced with this type of measurement and you have a certain test sequences that you want to do, for example, to save different test sequences, the advanced mode gives the user all the options and freedoms to measure manually or to create custom sequences to perform automated measurement. So like again, it addresses the expert user with the need for complete freedom of choice for all the parameters of the measurements. So basically, it works in a table format, and you keep adding columns to this to this space here. You keep adding columns, and each column will represent a different sequence, and then that in this tab right here, the sequence tab, you'll set up all these columns, and then you can just run your test, and these could be saved, and you can always have that there, just so you can move quickly from device to device. And again, all the test measurements will show up after each successful measurement. Your test measurements will be displayed in the results screen that could be accessed from the home screen. You can have it either in table format, will give you each test with, obviously depending on how you define the name and serial numbers of your test. So it will give you a time and date stamp, what sequence was measured, what type of connection, all the labels, and all your values. Alternatively, you can also, if for example you will be doing a frequency sweep and you want to have a graphical visualization of your results, you could also customize this graph by putting on your y-axis what value you want to see against your x-axis. For example, in this screen, they plotted how dissipation factor is changing depending on variable frequency from 50 to 400 hertz. So you have two choices. You can see it on a table, or you can go ahead and see it as a graph. And again, this is just a good, powerful tool to analyze your measurements on site. You don't necessarily have to transfer it to a USB and put it into your Excel spreadsheet. You can do it on the instrument on site. And then later on, when you have a little bit more time, you can sit and do a further analysis at a computer. This will also help you gauge whether or not there have been any errors in your test setup. So if you have different measurements that kind of look off, then it's easy in the table, for example, to note that difference quickly and maybe run a test a second time to verify. So right now, before we get into some other information on how to set up the MIDAS, I'm gonna play a short video that will kind of go through the operation of the MIDAS Micro.
We will walk through a detailed demo of operation for the MIDAS Micro. In this video, we will test a 2-winding transformer. All tests must be performed with the DUT completely de-energized and isolated from its power system. Testing will involve energizing the DUT through the MIDAS Micro, which can produce dangerous and life-threatening voltages and current levels. Extreme care and safety measures must be taken to avoid contact with the DUT and MIDAS Micro connections during testing. To begin, first connect the green and yellow safety ground cable to the MIDAS Micro. After the unit is properly grounded, connect the remaining test leads and high voltage output cables. Finally, connect the mains power input connection. This should always be the last step in setting up the instrument. Once the unit is powered on, the user must read and confirm important safety information. The MIDAS Micro has 3 modes of operation: guide, basic, or advanced mode. For the purposes of this demonstration, we will select guide mode. Next, select the type of transformer to test. We will use a 2-winding transformer as an example. Then, select C and tan delta, and all relevant test parameters. When performing these measurements, the low voltage terminals should be shorted together on one side of the transformer, while the high voltage terminals should be shorted together on the other side. To connect the MIDAS Micro to our transformer, first connect the high voltage supply cable to the high voltage winding that we just shorted together. Next, connect input A to the low voltage windings, which we've also just shorted together. Finally, connect the high voltage ground to the grounded transformer tank. Before starting the test, check that your test area is free of any hazards. Then, hold down the safety switch and click the high voltage on button. Note that the warning light turns on when high voltage is engaged. This is for added safety to both the operator and others in the area. After each measurement, the MIDAS Micro will prompt the user to confirm all connections to the device under test for the next measurement. Advanced mode is also available for users that want to create a custom sequence or have a special application not covered in the guide and basic modes. After all tests are complete, results are displayed in either numerical or graphical form. By using our data acquisition software, users have the option to save the results via USB or print the results with the integrated thermal printer. Once the necessary information has been recorded, you can end the test by powering the system off. For safety, use a grounding stick to discharge the device under test prior to removing connections. Disconnect all test leads from the DUT before disconnecting from the MIDAS Micro. The green and yellow safety ground cables should be the last leads disconnected from the MIDAS Micro. To recap, define the test. Power on the MIDAS Micro. Using the guide mode, select your device under test, the desired test to perform, and test parameters. Set up the test area. Follow the pop-up diagram to make the correct connections for your first measurement. Prior to starting the test, make sure the area is clear of all unnecessary personnel and obstructions. Perform the test. Step through the guide mode until all measurements are complete, making reconnections when prompted. Analysis. View your data in graphical or numerical form in the Analysis tab. Here you can compare against previous data, saving the results via USB, or print the results via the onboard printer. Complete the test. Power off the MIDAS Micro. For safety, use a grounding stick to discharge the device under test prior to removing connections. Disconnect all test leads from the GUT before disconnecting from the MIDAS Micro. The safety ground cables should be the last leads disconnected from the unit. Today's MIDAS Micro is the smallest and most compact insulation diagnosis tool on the market. Inquire today and we would be happy to provide you with a free quote.
All right, thank you. I hope you enjoyed that. That video basically recaps everything that I mentioned up to this point. And as you can tell, it's quite simple. It's very hassle-free. So so next, what I want to do is I want to get into just a quick before we go into questions, just a quick review of a example for a two winding transformer like you just saw. So like we mentioned, we want to short the high voltage and low voltage. If you have a neutral bushing, you will disconnect that from ground and then short it with the other bushings, and then you can go ahead and start your measurement. So for a two winding transformer, just quickly here, if we want to do the high to low voltage capacitance in 10 delta, we'll connect our high voltage lead. This is the black line right here to our high voltage, our measuring cable to our low voltage, our high voltage ground to the tank, and then of course the safety ground. And we'll choose UST, and we'll use, since we chose the measurement channel A, we'll do UST-A, and that'll give you your measurement for the high to low voltage. Similarly, for a for the high voltage to ground, we'll maintain our connection on the high voltage and low voltage as previously described. But in this mode, what we'll do is that we'll choose grounded, since we want to get the high to ground, the GST mode, and what we'll do is that we'll use the guarded A and B. So guarded A and B will basically take any signals that are generated to these measurement channels and take them out of the measurement circuit. And there we'll have our high voltage to ground capacitance in 10 delta. And once we do our low voltage, what we'll do is that we'll switch our high voltage cable, we'll put that on the low voltage, and the measuring will go on the high. Again, we'll use grounded specimen test, guarding A and B, because we do not want to have any other capacitances included in our measurement, and you hit start. I mentioned earlier about motors and generators and having higher capacitance devices or specimens. For that, we also offer the MIDAS 2881 or 81G with the MIDAS 2881. You can include an external resonating inductor, which will give you it'll let you test for up to 1.41 microfarads. So it really opens up the range to include your rotating machines. And the 2881G is specially designed for generators because it will go up to 15 kV, which is perfect for 24 kV class voltages. So we have also that. And if you joined us last in July for the 2293, which is our transformer winding analyzer, if you have both of these instruments, you basically have a complete transformer test solution. Again, if you have any questions, we'll try and get to them quickly. And then if not, if you don't have any questions, can't think of anything right now, you could always send your inquiries to our email at hvsales@hvtechnologies.com. So will that is the that will close out our presentation for today.